This is a video from section 7.2. Recall, sine squared x plus cosine squared x is equal to 1. That's the Pythagorean identity. Now, for number 2, start with sine squared x plus cosine squared x equals 1. And what we're going to do is we're going to divide both sides by cosine squared x. So, now, one thing to notice is that sine squared x divided by cosine squared x is equal to tangent squared x. So that's where I'm getting the first term. Cosine squared x divided by cosine squared x is 1. And 1 divided by cosine squared x here is equal to secant squared x. And that's where I get the term on the right-hand side. So your second identity is tangent squared x plus 1 is equal to secant squared x. And then by the same token, I'm going to start with sine squared x plus cosine squared x is 1. Divide both sides by sine squared x. And when you do that, you get 1 plus cotangent squared x is equal to cosecant squared x. And so what I want you to get out of this is that sines and cosines sort of go together, tangents and secants, and cotangents and cosecants. That's how we pair these off. Now, with that in mind, what we're going to do is we're going to evaluate the integral. And I want to give you insight on how we deal with these. So let's start off with example 1. Well, suppose I give you this one. The integral of cosine to the 6th y times sine to the 3rd y dy. And the way I attack a problem like this is I have a cosine to the 6th y and I have a sine cubed y. And what I want to do is I want to save off a sine of y if I could. So I'm going to write sine cubed y is sine squared y times sine of y dy. But if we go back to this first Pythagorean identity, I notice that I can solve for sine squared x, right? And that's exactly what I'm going to do here. So I'm going to rewrite this factor as 1 minus cosine squared y. And I want you to watch what happens. So this is the integral of cosine to the 6y times, now again, I'm going to replace sine squared y with 1 minus cosine squared y. And then I'm going to multiply by sine of y dy. And so this is the integral of cosine to the 6y minus cosine to the 8th y times sine of y dy. And this right here, I could use a u substitution. So this is what it's going to boil down to. So I'm going to let u be cosine of y. du is negative sine y dy. So if I solve for sine of y dy, I get negative 1 du. And so I'm going to put the negative 1 on the outside of the integral, and what I'm going to be integrating is u to the 6th minus u to the 8th, and this now becomes du with that negative 1, that is. And so I'm going to integrate here with respect to u. And so this is negative 1 times 1/7 u to the 7th minus 1/9 u to the 9th plus a constant c. And so I'm going to distribute the negative in. So I get 1/9 u to the 9th minus 1/7 u to the 7th plus c. But remember that u is equal to cosine of y. So if I substitute that in, I get 1/9 cosine to the 9th y minus 1/7 cosine to the 7th y plus c. And that's how you do the first example. If we take a look at the second example here, suppose I give you this one. The integral from 0 to pi over 4 of sine to the 5th x dx. Now, when you see an odd power like that, a really good strategy is I want to save myself a sine of x. Okay? So the way this is going to work is you're going to go from 0 to pi over 4 of sine of x times cosine, oh, excuse me, not cosine. You're going to take sine of x times sine to the 4th x dx. So you notice how I saved off the sign. And so this is the integral from 0 to pi over 4 of sine of x times, now if you don't mind, I'm going to write this as sine squared x to the 2nd power dx. You may not need that second line, but I want you to make sure we understand that sine squared x to the 2nd power is sine to the 4th of x. And so this is the integral from 0 to pi over 4 of sine of x. And so I'm going to rewrite sine squared x as 1 minus cosine squared x to the 2nd power dx. Again, we're going to do a u substitution. We're going to let u be cosine of x. du is negative sine x dx. Okay? Now, sine x dx is negative 1 du. Now, we have to transform our limits from x to u. So when x is 0, u is cosine of 0, which is 1. And when x is pi over 4, u is cosine of pi over 4, which is square root of 2 over 2. And so what I end up getting is negative 1 times the integral from, now, I'm going to go from 1 to square root of 2 over 2 of 1 minus u to the 2nd du. And that's to the 2nd power, by the way. Now, I could switch the limits and change the sign. So I'm going to go from square root of 2 over 2 to 1 of 1 minus u squared to the 2nd du. Now, I'm going to expand that out. So I'm going to go from square root of 2 over 2 to 1 of 1 minus 2u squared plus u to the 4th du. And that's going to be u minus, okay, so it's a straightforward integral from here. 2/3 u to the 3rd plus 1/5 u to the 5th, evaluated from square root of 2 over 2 up to 1. Now, if I plug 1 in, I get 1 minus 2/3 plus 1/5. If I plug square root of 2 over 2 in, I get square root of 2 over 2 minus 2/3 times square root of 2 over 2 to the 3rd plus 1/5 times square root of 2 over 2 to the 5th. And so the common denominator in the first one is 15. So I'm going to write 15 over 15 minus 10 over 15 plus 3 over 15. So that's for the first one. And then I'm going to subtract square root of 2 over 2. So we have to do a little bit of simplifying. Minus 2/3 times square root of 2 to the third is 2 square root of 2. And then I'm going to divide by 8. And then I'm going to add 1/5 times square root of 2 to the fourth is 4. So I get 4 square root of 2 divided by 32. So this is 8/15. So it's very calculation heavy, as you might notice. And then I get square root of 2 over 2 minus square root of 2 over 6 plus square root of 2 over 40. And again, it's going to be up to your instructor how far they want you to simplify. If you look here, the LCD between 2, 6, and 40, it's going to be 120. So you get here, you're going to get 8 over 15 minus. Now, the LCD between these three terms is 120. So I'm going to get 60 root 2 divided by 120 minus 20 root 2 divided by 120 plus 3 root 2 divided by 120. Right? And so your answer here, so you get 8 over 15 minus, that looks like 43 root 2 divided by 120. And if your instructor wants the same denominator, which would be fine, you would get 64 minus 43 root 2 divided by 120. And that would be the answer for this one. Let's take a look at example 3. Suppose I give you this one. Suppose I have the integral from 0 to pi over 2 of sine squared x cosine squared x dx. So if you notice, neither one of them is raised to an even power. So I'm not able to save off a sine or a cosine. So the question is then, how would we deal with something like this? So this is what I would do. I would write this as sine of x cosine of x to the second power. Okay? Now, recall. Sine 2x is 2 sine x cosine x. So if I divide both sides by 2, I get 1/2 sine 2x. So we get the integral from 0 to pi over 2 of, you get 1/2 sine 2x to the second power dx. That's what I would do. And then here, this is the integral from 0 to pi over 2 of 1/4 sine squared 2x dx. Okay, so I'm just squaring each term, or each factor, that is. Now, sine squared x is 1/2 of 1 minus cosine 2x. And so what I'm going to do is I'm going to replace x with 2x. And I'm going to pull that 1/4 to the front. So we get 1/4 the integral from 0 to pi over 2 of, now, here I'm going to take 1/2 of, now x gets replaced with 2x. And so this here becomes 4x. So it's 1 minus cosine 4x dx. And so here I get 1/8 the integral from 0 to pi over 2 of 1 minus cosine 4x dx. So this is 1/8 times x minus, now the integral here is going to be 1/4 sine 4x, and this is evaluated from 0 up to pi over 2. Now, I'm going to replace x with pi over 2 and replace x with 0. So I'm going to take 1/8 times, plug in pi over 2, I get pi over 2 minus 1/4 sine of 2 pi. If I plug in 0, everything zeroes out. And so that's it. So the answer here, sine of 2 pi is 0, and so your final answer is pi over 16. That's example 3. If we take a look at example 4, suppose I give you this one. Sine x, well, I'm going to do this one. So let's try this one. So we're going to do sine squared x sine 2x dx. Now, what you want to do here is you want the arguments to be the same, if at all possible. And so I'm going to write sine 2x is 2 sine x cosine x. Okay? And so this is the integral of sine squared x times 2 sine x cosine x dx. And so I'm going to pull the 2 out in front, and we get sine cubed x cosine x dx. Let u be sine of x. du is cosine x dx. So notice in this situation, a cosine has already been saved for us. So we're okay. And so this is twice the integral of u cubed du. And so this is 2 times 1/4 u to the 4th plus c. But u is sine of x. And so the final answer here is 1/2 sine to the 4th x plus c. And that was example 4. Let's take a look at example 5. Now, what if I gave you something like this? Well, suppose I had cosecant to the 5th x times cosine cubed x dx. Now, cosecants and cosines don't go together, but sines and cosines do. That's how I think of this. And so what I'm going to do is I'm going to rewrite this as cosine cubed x divided by sine to the 5th x dx. There's a couple ways you can go about this. what I'm going to do is I'm going to save off a cosine. So I'm going to write this as cosine squared x times cosine x in the numerator. And in the denominator, we still have that sine to the fifth x dx. But I'm going to write that cosine squared x as 1 minus sine squared x. So we get 1 minus sine squared x times cosine x divided by sine to the fifth x dx. And so here, I'm going to let u be sine of x. Remember, I saved off a cosine. That's what you want. And then it's just really u substitution the whole time. So over here, I get 1 minus u squared divided by u to the fifth du. And so I'm going to split off that fraction into u to the negative 5 minus u to the negative 3 du. Okay? And then negative 5 plus 1 is negative 4. So this is negative 1 over 4 u to the negative 4 minus a negative 1 over 2. Negative 3 plus 1 is negative 2. U to the negative 2 plus c. So I'm going to get rid of those negative exponents. So you get negative 1 over 4 u to the fourth plus 1 over 2u squared plus c. But u is sine x. So when I plug that in, I get negative 1 over 4 sine to the fourth x plus 1 over 2 sine squared x plus c. It really does depend on your instructor. Your instructor may want you to express your answer this way. Negative 1/4 cosecant to the fourth x plus 1/2 cosecant squared x plus c. That is possible that your instructor may want you to write them in terms of cosecants. So it's something I want to make sure you're aware of. That was example 5. Let's do one more example for this video. See if we can fit one in. Suppose I give you this one. Suppose I give you the integral of sine x times secant to the fifth x dx. And just like in example 5, sines and secants don't go together, but sines and cosines do. So I'm going to write this as sine x divided by cosine to the fifth x dx. Okay? And in this situation, I'm going to turn it into this. So this may not be obvious, but I'm going to write this as sine x over cosine x times 1 over cosine to the fourth x dx. So really what I'm going to do is I'm going to turn this into tangents and secants. So notice that sine x over cosine x is tangent x. And then 1 over cosine to the fourth x is secant to the fourth x dx. Now, with tangents and secants, you have to save off. Well, there's actually a couple ways you can do this. Now, I want you to watch this. Now, over here, I'm going to write this as secant cubed x. So I'm saving off a secant. So I'm going to write this as secant cubed x times secant x tangent x dx. So I set myself up perfectly for a u substitution. There is another way to approach this, by the way. And so I'm going to let u be secant x. du is secant x tangent x dx. And so this is the integral of u to the third du, which is 1/4 u to the fourth plus c. But u is secant x. So your final answer here is 1/4 secant to the fourth x plus c. Now, one thing I want you to note, so I was over here at tangent x secant to the fourth x dx. And what I was about to do is I was going to tell you that I could write this as tangent x times secant squared x times secant squared x dx. I saved myself a secant squared x. Why? Because the derivative of tangent x is secant squared x, and then I know I could rewrite that other secant squared x. So in other words, I could write this as tangent x times 1 plus tangent squared x times secant squared x dx. Totally legal. And I could let u, I won't go through the whole thing, but I could let u be tangent x, and du is secant squared x dx. And that's a totally legal way to do that problem. Okay, that'll conclude this video for section 7.2. This is for a Calculus 2 course, Math 401. Okay, thank you.